So we're looking at applications of using E. So we're going to be using logarithms to solve things in equations that have E in them. So you'll want to have your calculator handy. All right, so here's what we're going to do. I have frozen the screen, so give me a second. Here we go. So applications of E. Starts with Tara's parents invested $5,000 in an account that earns 11.5% compounded continuously. So this is completely fictitious. These accounts don't exist. But this would be like a maximum you could get. How long will it take for the investment to reach $10,000? So the formula that we learned in a previous class.
What measurement of time is being used?
That's what we're getting ready to talk about. Okay, so this is the formula that we learned in a previous class. Actually, it was last year for the group I have in here. That we did for compounded continuously. It is a different formula than if it's compounded daily, monthly, quarterly, etc. And so your principal goes here, so that would be the $5,000 she invested. E, the interest rate's 0.115, which is also fictitious. You'll never find that. And then the time we're just going to call T, and this would be in years. And then we're looking for when that's going to equal 10,000. So this is the formula. We've used it in the past to find total amounts. Now we're going backwards. We're going to use logarithms to solve this. Yeah. So just like we learned in the last two lessons, when you guys have a number in front of your powered thing, you're going to divide to get rid of that. A lot of you are trying to subtract. You need to divide and divide. So 10,000 divided by 5,000 is 2. So I have 2 equals E to the 0.115 T. So to solve this, we want to put it into log form. So this would be log base E of 2 equals 0.115 T. But log base E has a special name, and it has its own button. ln. It's ln. So this would be natural log of 2. And then to solve for T, you would want to divide by the 0.115. And then you can just type that into your calculator. Sorry, guys. Natural log of 2 divided by 0.115. And it comes out, it rounds off to about 6 years.
That's really fast.
Yep. So this would be compounded continuously. So that was more than compounded daily with a really high interest rate. So it's not a savings account. Shh. All right, let's look at number 2. Nuclear energy derived from radioactive isotopes can be used to supply power to space vehicles. They do this. They have tiny little nuclear reactors in them. The output in watts of the radioactive power supply for a certain satellite is given by the function below. How much power will be available at the end of 180 days? So what we're going to do is put 180 into this, and what it doesn't tell us is that we're measuring this in watts. So we'll figure that out. So we're just going to put this in for T. So you'll have 40 times e to the negative 0.004 times 180. If you're putting this into a calculator, you can type the whole thing in by doing 40 times e to the negative 0.004 times 180, like that. And it'll round off to about 19.5, so about 19.5 watts. Okay. Sorry. So about 19.5 watts is how much power is still available. If you're looking at this formula, you can actually tell how much power was originally available. So this number right here is how much you started with. So that 40 in front would mean that you started with 40 watts. This story problem was longer originally. I shortened it to fit it in the notebook. So the 40 is the 40 watts that you started with, which we kind of need to know to get to the next part. So it says, using the same equation as in the last example, how long will it take for the amount of power to be half its strength? So we were close here because 19.5 is close to 20, which would be half of 40, but not quite. So
Well,
what we're going to do is, so we're starting with 40 watts.
I know, but how do we know when it says how long for it to be half its strength? Does it mean half the 40 or half
Half of the 40.
5? It doesn't
Half of the
matter.
40. So we're looking at, so from the original, half of its original strength. There, now it'll make you feel better. So 20 equals 40 times e to the negative 0.004t.
I didn't throw anything.
I just saw something. All right,
I went through the air.
so we're going to solve for t up here.
Okay, so divide by 40.
So divide by 40, and you get a half or 0.5, which makes sense because we're looking for half. And you have e to the negative 0.004t, and then we're going to put it in log form to solve it. So this would be log base e of 0.5 equals negative 0.004t. But remember that log e is just natural log, so if you want to skip to that, you can. Natural log of 0.5.
Do you think Riley fell in?
Shh. You're up to about 3 marks at this point. I should send you to the office. You can decide on whether that needs to happen or not. All right, so we are dividing now by negative 0.004 to solve for the time. And it comes out 173.3 days. So we knew 180 was close. But to be at exactly half, it would be somewhere in the middle of that 173rd day is when we would have half of the wattage left. Okay? So you're going to encounter a lot of weird formulas that all have the same basic component, where you have an original amount or a principal, some kind of growth or decay rate, and time and E involved. They're all going to solve basically the same way, but they're all a little bit different and have different contexts. All right, so going down to this next section, this is just sort of showing you how you can set up decay and growth problems that involve E. So if K is positive in that power, that's growth. If it's negative, that's decay. A is your original amount, and whatever is over here is the final amount. All right, so radium-226, which can be used for cancer treatment and as an ingredient in fluorescent paint, which seems like two very different things, but it's true, decomposes radioactively. Its half-life is 1,800 years. So that means in 1,800 years, half of it is no longer radioactive, half of it is. That's what half-life means. So it says find the constant K you would use in the decay formula for radium. Use 1 gram as the initial amount, and then determine how much radium-226 will be left after 500 days. So there's not a lot of room at the bottom of here, but we're going to do quite a bit of work. So we're going to start with 1 gram, and we're going to go to its half-life. So I'm going to start with 1 gram times E, and we don't know what K is. They're telling us to find that so we can actually write an equation for radium-226. We do know that its half-life is 1,800 years, so I'm going to put that in for the time. And then the amount left would be half of 1, so you could write it 1/2 or 0.5. I'm just going to use 0.5. So we're starting with 1 gram. We're ending with half after 1,800 years because that's the half-life. So then you could divide by 1, but really that's not very exciting. We could just skip forward to rearranging this. So we'd have log base E of 0.5, which we've done a couple of now. That would just become natural log of 0.5 equals K times 1,800. And so to find K, we would just need to take that and divide by 1,800. And it comes out to be a tiny little decimal. It is negative 0.000385 is the constant K that we would use for radium-225. So then the equation would be, we would say the amount after a certain amount of time would be equal to your original amount times E to the negative 0.000385 T. So basically we just put this together so that we wouldn't have to use the half-life formula we did in the last lesson. this will approximate the same thing. So it's another way to do the same kinds of problems. So there's the equation that it asks for. And then it says to see how much will be left after 500 years. So we'll put 500 into the equation. So we would just have e to the negative 0.000385 times 500. Again, if you're putting that in your calculator, you would put all of that power in parentheses, and it comes out about 0.82 grams is what you would have left out of the 1 original gram. I should have put a 1 there in front, but I was thinking, oh, if I multiply by 1, it really isn't that exciting. But that's my original amount was 1. We'd have 0.82 left. So basically you have 82% left of however much it is. We just happen to start with 1, so we get 0.82. All right, moving along. We're going to look at something that's not sciencey on the next page. So those are sort of our trip into science for a little bit. The city planners in Bakersfield, California are studying the current and future needs of the city. Large cities do this a lot. The sewage system they have in place now can support 250,000 residents. The current population of the city is 175,000, which is up from 106,000 10 years ago. So 10 years ago it was 106,000. Now it's 175,000. That's the information that they have. Because the U.S. Census is done every 10 years, that's probably why they have those two particular numbers handy that they know for sure are correct. It says, assuming that the population will continue to grow at this rate, when will the sewage system need to be updated? So we can model this with a continuously growing Model 2. So we could start by saying, okay, right, we are started with 106,000 people 10 years ago. Multiply it by E times some unknown growth factor. We don't know what that is, but it's been 10 years. And then now we're up to 175,000. And if we set it up this way, we can figure out what that growth factor is, write an equation, and then we can figure out when it's going to have to be updated from there. So this is just an equation we're going to solve for K. What would we do first?
Divide by 106,000.
Good. Divide by 106,000.
I don't know if I believe you.
Okay, so then I have e to the, I'm just going to say to the 10k equals, and this comes out to be about 1.6509. You do not want to round this off very much. You don't want to have a lot of rounding error. You could keep it as some sort of weird fraction that's reduced. If you were super worried about this, if you were actually doing this math for Bakersfield, California, you would probably keep a little bit more. Okay, so when we solve this, we're going to rearrange it and do a natural log. So natural log of 1.6509 equals 10k. So to solve that, then you divide by 10. And we'll find out that k is about 0.05. So we could do an equation. We could call it P for population. Would be 106,000 to start with, and then E. Oh, I'm sorry. We want to start from where we are now, not what we were later. So 175,000 is where we want to start because that's where we're at now. Times E to the 0.05 T. So this would be any number of years from the present date. And so this would be an equation that we could then use to figure out when the sewage system needs to be replaced. So we have 175,000 people now. It can only support 250,000. There's only so much junk that can get shipped through those pipes. So before things start backing up and it becomes not so good. So what we're going to do is take this equation then and set it equal to 250,000 and solve for the time. So it solves just like all the others we've done. We divide by the number that's in front of the E first. So you divide by 175,000. You have E to the 0.05 T equals whatever that number is, which I have as about 1.4286. It kind of keeps going. It's a few decimals. And then we can rearrange it to solve. So we'd have natural log of that number we just found equals 0.05t, and then get t by itself by dividing by 0.05, and it comes out roughly 7.1 years, which is not very far in the future. And that's a project that would take a while. So if it has to be in place in 7 years, that's when somebody would start going, okay, how long would it take to replace all of this? They'd probably start doing sections pretty quickly. And this is the kind of math they would take into a city planning meeting and say, okay, we've got to get on this now. We've got to start setting money aside, start doing this section, this section, this section. How are we going to divide it out? Who's going to do the work? All of this. Big cities hire math people to figure this stuff out. Believe it or not, there are jobs they pay better than mine. All right, B says, how many people will this new system have to accommodate for the system to last 15 years before being replaced? So we're talking like after we've replaced it to this system, they're trying to figure out if we, how long, if the, let's say, how many people will this new system, so how many people will this accommodate for it to last 15 years? So basically we need to know how many people we'll have 15 years from now. So we can use this population equation that we had. So 175,000 is where we're at now, times e to the 0.05, and then we'll just put in 15 years and see how many people we're going to have in 15 years. And I rounded this off to the nearest 1,000 people because you know this is an estimate, right? So I put 529,000. Honestly, if you were doing this, they'd probably say 530,000 and round it off even more. Not very many significant digits.
That was awesome, I guess.
So, so it's a lot of people. If they want the new system to last 15 years, it's got to be able to handle this many people. And then if they're going, okay, we don't want to replace this for 50 years, they have to really get busy and figure out what they have to do with that system. Okay, so we're going to leave the last problem for practice, so that's it.
Yay.